So ocean has a big role to play in carbon cycle as well, especially because it has so much of the surface area of the planet, as well as it produces so much primary productivity, bottom of the food chain, which supports fish and the rest of the marine ecosystem and supplies a lot of food to humans on land. The primary productivity on land and ocean are almost similar in terms of let's say paragrams of carbon that is fixed into organic matter, but in the ocean there are a longer food chain in terms of secondary production, tertiary production, and so on and so forth, because ocean is distributed much more in the vertical, and phytoplankton are eaten by zooplankton, zooplankton eaten by small fish by big fish, and so on and so forth. So that's just something to remember. As for the role in the ocean, role of the carbon, role of the ocean in the carbon cycle, the very special thing is that the ocean has the ability to move dissolved carbon into multiple components, multiple boxes, which gives it the so-called ability to buffer against change in carbon dioxide. Okay, so if obviously when you have CO2 plus H2O, we said in photosynthesis you get carbohydrates, but when you dissolve it in water you get carbonic acid. In the ocean CO2 is highly soluble in water, right? So when the CO2 from the atmosphere dissolves into the ocean, it is immediately moved into bicarbonate, and H plus ion is released, and that also then is split into carbonate ion, CO3 minus minus, and then another H plus is released, so you end up with CO3 minus minus plus 2H plus. So this is like having some income, but you are able to spend more than you can because you got a way to or you spend more than you earn by whiling it away into different, I don't know, whatever the analogy you want to use. Okay, so what happens in the ocean then is, if you have atmospheric CO2 dissolving into the ocean, you create H2CO3. Immediately that goes into HCO3 minus and H plus, and HCO3 minus goes into carbonate ions and another H plus. This is a critical part of the reaction. As we said, the ocean water doesn't get easily saturated with CO2 because it doesn't stay in H2CO3. It gets moved into HCO3 minus and CO3 minus minus. What actually happens is that as CO2 in the atmosphere increases, the reaction rates here cannot keep up with the H2CO3 being formed. So we will see in a minute that actually that begins to lead to the consumption of CO3 minus minus and produce H plus and lead to acidification or pH decrease, which is bad news for all these things that are floating around here that are forming calcium carbonate shells, diatoms and various other shell forming organisms, corals, and so on and so forth. So you can look at it in a schematic way this way. So let's say we are looking at late 1800s, where the acidity or pH was lower because atmospheric CO2 was lower. So we are looking here at the pH scale. The red scale is where you are getting into acidification territories for the ocean. So lower concentration of atmospheric CO2 in the late 1800s led to a certain range of H2CO3, H plus, and HCO3 minus, and the carbonate ions are used by these corals, mollusks, and other marine calcifiers to form their shells. If they have to remain in shell form in the surface waters or somewhere in the water column. That means they should not dissolve, which means the waters are super saturated with calcium carbonate, which means there is enough carbonate ion to keep the calcium carbonate supersaturation. But if we look at what is expected in 2100, we'll see in a minute what is already happening. Acidity is going to increase, so you can see that the pH is going to drop below 8. Already pH has dropped from about 8.2 on average to 8.1 or so, as we will see. Higher concentrations of atmospheric CO2 are going to lead to more H2CO3. Then the water's ability to split into HCO3 minus and CO3 minus minus is going to be slowed down. So that means CO3 minus minus carbonate ion is going to be consumed by acidification, so that's going to affect calcifying animals. So fewer and smaller marine calcifiers are going to result from this. Okay, so this is how NOAA would put it: ocean acidification. How will changes in ocean chemistry affect marine life? CO2 absorbed from the atmosphere. So here you have these calcifiers, the healthy one, the not so healthy one, and the one that is going to be seriously disabled in surviving with calcium carbonate shells. So the net reaction is CO2 plus H2O plus carbonate ion converting to 2HCO3 minus. So as you increase CO2 and the buffering reactions cannot keep up with the increase in CO2, then you are going to end up consuming carbonate ion and lead to these situations. So consumption of carbonate ions impedes calcification in the ocean. So you can see this nicely in this example from PMEL as well. So we have CO2 gas that is dissolving, forming CO2 aqueous hydrated CO2 molecules, which are going to dissolve and form carbonic acid. So in the pre-industrial time scale, we had 280 ppm, and let's say H2CO3 was 8 units, whatever the units, we will not worry right now. So H2CO3 was splitting into H plus and bicarbonate, with a bicarbonate at 17 units. A bicarbonate would split into carbonate at producing 268 units. Typically these are micromoles per meter cube or so, so you can check the unit. I should have put it here, sorry about that. So this together adds up to what we call DIC, or dissolved inorganic carbon. So H2CO3, HCO3 minus and CO3 minus minus, and a pH of 8.15. We'll see that ocean has maintained this pH for tens, if not hundreds of millions of years. Well, at least tens of millions of years. But with doubling of CO2, you will increase this aqueous CO2 to 560. Carbonic acid will not completely double. It will reach 15, because you are going to move it into HCO3 minus and CO3 minus minus. But the increase in HCO3 minus is here, whereas CO3 minus minus is decreased substantially. So you end up with DIC that is much smaller than the increase in CO2, and pH is going to drop. And if you triple the CO2, you know the story, that it's going to triple the aqueous CO2. H2CO3 is here, HCO3 minus, and CO3 minus minus decreases even further. DIC doesn't decrease as much, and the pH drops again. So this is quintessential ocean acidification. So other than all the global warming and so on, ocean acidification is a direct consequence of increase in atmospheric CO2. So we can also see it this way for long-term balance and how pH has been maintained. So ratios of carbonate species concentrations as a function of pH. So we are looking at the pH scale here. Currently, average seawater has a pH of 8.1. Therefore, most of the carbon in the ocean is in the form of bicarbonate, HCO3 minus here. Addition of anthropogenic CO2 decreases pH. So this is maintained basically by dealing with the increase or decrease of CO2 due to natural variability like ice age, deglaciation, continental movements and other things, because they happen at a certain time scale. When we increase CO2 very rapidly, then we already saw that this adjustment of HCO3 minus and CO3 minus minus doesn't keep up, so we end up moving towards lower and lower pH values. Okay, so here is maybe I should come to this later on, but there is the other concept of alkalinity. So in the ocean, it's not just pH. Alkalinity is the total number of H plus ions, or the ability of the fluid to neutrify acid. So if you think about atmospheric CO2 and the reaction we talked about, we have carbonic acid, bicarbonate and carbonate, but the ocean also has lots of other ions that contribute to what is called total alkalinity. So total alkalinity of the ocean is what determines the CO2 balance in the ocean, and on longer time scales it will also affect the atmospheric CO2 balance. So there are lots of details, and in fact in my carbon cycle course I have lots of the details that we are not going to get into. So this also tells you that you cannot create ocean water by simply dissolving salt into the water, because you need alkalinity, which becomes very critical for understanding the carbon cycle and the buffering ability of ocean against increasing CO2. So let me come back to the carbon cycle in the ocean with a bit more detail in the next podcast. I will leave it here because ocean acidification is an important topic by itself. The concept of alkalinity is quite complicated. I showed you a simple figure. There are very nice articles written by people like Boom Boom Zibi, what's his name, Richard Zibi or whatever, in Hawaii. So there are many, or Sarmiento, Gruber, Mick Follows. There are many people who are carbon cycle experts and explain alkalinity very well. It is an important concept, but we'll come back to carbon cycle in the ocean and look at how carbon gets moved around by the circulation in the ocean and biology in the ocean. So we will see the concept of biological pump and solubility pump in the ocean. Okay,